Today we're looking at how gases behave as temperature changes, and particularly we're looking at how the volume of a gas changes with temperature. Charles's law says that gases should get larger as temperature increases, and they should expand as temperature increases, and the gas should contract as the temperature reduces. And this is expressed mathematically, that the ratio of a hot temperature to a cold temperature is equal to the ratio of the volumes, the volume at the hot temperature to the volume of the cold temperature. And this is a fundamental theory, this is a fundamental description of gas behavior that leads us into a fundamental theory of how gases behave at a microscopic level. This is a macroscopic relationship that we see in the lab today. We're going to use a hot temperature of 100 degrees Celsius and a cold temperature of 0 degrees Celsius because we can make those in the lab using water. The temperature scale used by Charles is not the Celsius or Fahrenheit scale, it's the scale in Kelvin, so that the temperature at 100 degrees Celsius becomes 373 Kelvin, the temperature at 0 degrees Celsius becomes 273 Kelvin. And we're going to look at a pop can that has about a volume of about 360 milliliters and try and predict what its volume is when we cool it. So we're going to heat a can to 100 degrees Celsius. The air in the can is going to be at 100 degrees Celsius. It has a known volume. And then we're going to put it in the cold water bath and find out what its volume should be. Charles's law lets us predict this. It says we start with the ratio of the volumes. The 360 over the unknown volume, x, should be equal to the ratio of the temperatures, the hot temperature to the cold temperature. And I take that ratio, it's 1.37, or approximately 1.4. And then if I solve for x, we predict that the volume of the can, when it shrinks because it's colder, it should be 363 milliliters. This is an example of the original can we're using, which we measure as having an air volume of 360 milliliters. Here's an example of the shrunk can. And the shrinking occurs because of the pressure of the gas in the atmosphere pushing down on the can. And so it's not that the metal is shrinking, it's that the actual air volume in the can is shrinking, and the can contracts with it because we've got these very thin-skinned aluminum cans. We'll also look at an extreme version where we allow water in the can, and something slightly different happens, but we get a much more spectacular shrinking of the can. And I keep tending to close my eyes as I talk, don't I? I don't know if that's obvious in the video.